In this video, we're going to talk about an electric potential across a cell membrane. So in general, we call it a membrane potential. So what does that mean? All living cells have an uneven charge distribution across the plasma membrane. And as shown here, it means that the outer surface of the cell has predominantly a positive charge, and inside of the cell has a negative charge, and this creates what's called the voltage. Voltage is a result of separating opposite charges and the voltage can be measured using instruments by scientists. So the average membrane potential for resting cells is about 70 millivolts, but this is an average, so it could change between different types of cells. So now let's talk about how is this charge difference created? What is responsible for creating a charge difference and also for having this particular voltage, average voltage across a cell membrane? There are three factors that determine the membrane potential, the voltage across the membrane. They're the three main factors. There are other factors that come into play in occasions, but the main three we're going to talk about in the next few slides. So the first, if you like, factor is a sodium-potassium ATPase pump. So that's a lot of words. What does that mean? Well, first of all, it's a pump. That means it moves molecules, specifically sodium and potassium, against their concentration gradients. It's an ATPase, so it's an enzyme that breaks down ATP. So the sodium-potassium ATPase pumps sodium, uses the energy of ATP to pump 3 sodiums. For every 3 sodiums that it pumps out of the cell, it brings in 2 potassiums inside the cell, such that if you start with a cell that has no voltage difference across its membrane, then this alone can, let's say, make the inside of the cell negative, outside positive, and usually the sign that we give to the number that indicates the membrane potential pertains to the electric sign inside the membrane. That's just the convention. So this sodium-potassium ATPase alone maybe brings down the membrane potential to -5 millivolts, and I'm going to play you a video here to see how it works. So this is the pump sitting in the plasma membrane. These are, you may see words here that are not English, but that's okay. It shows the process nevertheless. So these are supposed to be sodium ions sitting inside the cell. So it's using the energy of ATP to pump sodium out of the cell, and then it brings potassium inside the cell. So your cells, as you are sitting down on a chair, all of your cells, even if you're not spending a lot of energy, your cells are constantly pumping out. For every 3 sodium pumping outside of the cell, they bring 2 potassiums inside the cell. So if you think about, let's draw it to see what it means. So if this is a cell, this pumps sodium out of the cell and potassium inside the cell. So you're going to have not many sodiums inside, but lots of sodium ions outside. And then you're going to have lots of potassiums inside and few potassiums outside. So it generates a concentration gradient across the cell membrane. Now, why does it give the inside of the membrane a negative charge? Well, because if you put 3 positive ions out of the cell, you get 3 positive out and then bring 2 positive in, then you're going to have a deficit of positive charges inside the cell. So of course it makes inside the plasma membrane negative, and then outside of the plasma membrane positive. So therefore it generates an electrical potential. But this is not the only player. So let's see what else is involved. So the second factor is channels that are permeable to potassium, and they allow potassium to leak out of the cell. That's why we call them leak channels. So this movement follows the concentration gradient of potassium. So these channels will allow potassium to follow their concentration gradient out of the cell. Now this is a very busy slide, so let's go through it. First of all, remember we started at no membrane potential, sodium potassium ATPase brought it up to -5 millivolts, and then as a result of the action of this channel, then the membrane potential goes down to -negative millivolts. So why is that? Why such a big change? Well, let's take a look at what we have here. Here we have the sodium potassium pump right here. We have the leak channel here. We also have these ions. For now, I've masked the sodium ions outside the cell because we want to only focus on potassium ions. As you can see inside the cell, there's a lot of potassiums, and the outside a little bit, but you can see that potassium inside the cell is bound to these anions, and there's a lot of anions. If there was a gradient of anions, so you would have more of it inside the cell than outside. So potassium ions are bound to these anions inside the cell, and these anions could be things like phosphate or proteins that have a lot of negative charge. So let's see what happens when potassium leaves the cell. So let's take a few of them out. So let me get my pointer, and then so this potassium goes out. Oops. Goes out. Let's take another potassium out. Okay, and then now you can see that we have these negative charges that are sitting here without a partner. So therefore you're going to have an accumulation of negative charges on this side of the membrane, and that's why the inside of the membrane becomes more negatively charged. Now this negative charge kind of stops at around this number, and there is a reason for that, because initially, if you remember, we said that the cell has lots of potassium inside and a few potassium outside. Okay, and the cell membrane has kind of negative charges and a positive charges here. Now as the potassiums in the beginning, potassium follows its concentration gradient, so it moves out of the cell following its concentration gradient, so it keeps going. Okay, and it makes the inside of the cell more and more negative. But at some point inside the cell gets so negative that the electric attraction between the negative charges and potassium ions becomes so strong that it produces a force in the opposite direction. And finally, this number, it kind of stabilizes here when both of these forces are equal and opposite. Okay, this is something we call the equilibrium membrane potential for potassium. The third factor is the major factor is the sodium leak channels, which is basically the same kind of channels that allows sodium to leak into the cell following its concentration gradient. But we'll come back to this later. So let's again go around, see what happens. Let's see what we have in this image. So we have the sodium potassium pump, we have the potassium leak channel, and now in here we have the sodium leak channel. And I've already moved some of these potassium ions outside. So now we are at this number. But then remember that we said a lot of negative charges accumulate inside the cell, and that's a force of attraction to sodium coming in. So not only sodium can move down its concentration gradient, but it's also because of these negative charges, that's kind of an added benefit, added force to bring sodium in. So this happens very quickly. So therefore, we're gonna bring some, we're gonna bring some of these sodium ions inside, which are gonna come inside and start neutralizing some of those negative charges. But you may be asking, well, why doesn't sodium keep coming into the cell, and why does it stop at minus 70 millivolts? Now we're coming to the point that I said I'm going to come back to. The cell is much more permeable to potassium leak channels, and the concentration gradient across the cell for potassium is much steeper. So there are many more potassium leak channels compared to sodium leak channels. So in terms of leaking, these two channels, sodium is really no match to the potassium channel. So that's all fine. Potassium has more opportunities to get out, but this creates an interesting situation. As more potassium leaves out of the cell, then you get a buildup of negative charges inside the cell. The more potassium leaves, the more negative charge we get. So this creates a situation where we have so much negative charge inside the cell that these negative charges start slowing down the movement of potassium outside the cell. It doesn't stop it, it slows it down. At the same time, these negative charges pull the sodium ions inside. And finally, you get to a point where the rate of movement of potassium going out of the cell and the rate of sodium coming into the cell stabilizes. They become the rates become equal. So then that's why the membrane potential stays at minus 70 millivolts. This is the resting membrane potential. This is when you get to a place where the membrane potential is stable until something comes in and changes the distribution of ions across the membrane. Okay, you're going to be seeing a lot of graphs representing changes in membrane potential, and let's see what they look like, how we change the dynamics of these ions across the cell membrane. Here I have a cell, and then I have 3 channels in here. This is the ATPase, sodium potassium ATPase. This is a sodium leak channel, and this is a potassium leak channel. And I've shown the kind of roughly the unequal distribution of these ions across the membrane. So at this point, the membrane potential is 0. There is no difference in charge inside and outside of the cell. So let's see what happens when the sodium potassium ATPase starts pumping 3 sodium. For every 3 sodiums that it pumps out, it brings 2 potassiums in. Okay, and you can see that as a result of doing that, then we have a buildup of a kind of a tiny negative charge in here. So then what will the graph look like? Well, we start from 0 and we kind of go to -5. Okay? So now what happens to the graph when potassium starts leaking out of the cell using the link channels? So here it is, potassium is going out, keeps going out. As you remember, there are many potassium leak channels on the cell membrane, many more than sodium leak channels. So what's happening here? We see as the potassium leaves the cell, you get all these negative charges build up. So what happens to the membrane potential? It becomes even more negative inside as compared to outside. So then what does it look like in the graph? It will go, as we said in the previous example, goes all the way to -90. Okay, so what happened next? Well, sodium started coming in through the leak channels. Okay, and there's not that many leak channels as we said. So let's say we get maybe, just for comparison, one of them, because we don't have too many of them. Okay, so the inside of the membrane, it's still negative, but it's a little less negative. So then the graph shows it goes to -70. Now imagine that we have a particular kind of sodium channel that can be opened at will. Okay, so if we open it, if we wanted to, we can open this channel, and you can see that there's negative charges inside the cell. So that's a strong pull for sodium to come in. And also, let me just put this closer to here. And then there's also a concentration gradient, more sodium outside than there is inside. So these sodiums are going to start coming in through this channel. They start rushing in, and they keep rushing in. And you can see now the inside of the cell is more positive, outside of the cell is more negative. So what happens here? The influx of sodium causes the potential to go towards positive, because now the inside of a cell is more positive than outside. So you're basically flipping the script. Okay, how about we have a chloride channel? I didn't draw chloride here, but we can certainly draw it. So here's a chloride channel, and there is, let's draw, and there would, let's say, be some chloride inside the cell, but there is lots more chloride outside the cell normally. Okay, so what if we open this chloride channel and chloride comes in and rushes inside the cell? Let's see what happens. Well, the chloride starts coming into the cell, and what's happening? It makes inside of the cell more negative. So which direction does the graph move to? Towards negative. Let's say we're bringing so much that goes even lower than -90. So I hope this demonstration helps you connect changes in membrane potential as a result of ions moving across the membrane into a graph that you're going to be seeing a lot.